Hello, welcome everyone. Welcome to a new virtual tour of the European Southern Observatory, or simply ESO, its acronym. My name is Farid Char, and with the producer Hector Salas, we are going to be your guides during this trip to ESO Paranal Observatory. Just a little bit about me. I have more than 15 years of experience in astronomy outreach and education. I am one of the guides of the observatory, Paranal Observatory, since 2010. And one of my main hobbies is astrophotography. So ISO wants to be with you during these virtual visits and bring astronomy directly to your home or wherever you are. So please remember, you can send your questions or comments during all this streaming. So as I told you already, I am not alone. I am with the producer Hector Salas. So how are you, Hector?
Hi Farid, happy to be here once again. So I'll introduce myself. My name is Hector Salas. I'm a PhD student at the Leibniz Institute for Astrophysics in Potsdam, Germany. I work mostly with topics related to the circumgalactic medium, that is the environment that surrounds galaxies. And I have been a member of the guides team for Paranal Observatory since 2019. I started while I was doing my master's in Chile. And today I'll be the producer, so I'll be uh, controlling the pictures, the videos, but I will also be reading all your comments and questions. So please, if you have any doubts or if you want to send any greetings, just feel free to do so. And we will have some time during the tour to answer any question you might have.
Okay, thank you, Hector. So yes, we will be waiting for your questions or comments. So we will have some time later to answer them. Okay, so we are going to start immediately, and I want to help you to understand first the place of our visit. So we will begin with some information about the European Southern Observatory, or ESO. So ESO is composed of 16 member states. You will see a picture right now, and well, basically the headquarters of ESO are located in Germany, and also Australia has joined ESO, but in this case, as a strategic partner. Chile is the host state and home of all ESO observatories. Now, from the 60s, and with those objectives in mind, ESO has chosen one of the best places on the planet for astronomical observation, the Atacama Desert in Chile. So during this period, Chile started several site explorations in order to attract international observatories such as ESO to our country. As a result, Chile offered its territory and ESO did choose the more suitable areas. So the mission of ESO is to design, build, and operate astronomical observatories. And what for? To enable important scientific discoveries and incentivize the promotion and cooperation in the astronomy field. Now, right now, you will see a picture with the three um, observation sites of ESO in Chile. So here we have the Chajnantor Plateau, the site of the ALMA radio telescope. ESO is part of this radio astronomy observatory alongside other international partners. In addition, south of the Atacama Desert, at 2,400 meters above the sea level, we have La Silla Observatory in the Coquimbo region in Chile. So this ESO observatory is the home of several telescopes, such as the NTT, or the 3.6 meter ESO telescope. And this one is using the HARPS instrument. And HARPS is an exoplanet hunter. And finally, we have the place of our visit, the Paranal Observatory. This ESO observatory is the home of the Very Large Telescope, or VLT, the most advanced visible light telescope on the planet. In the next few years, we will also have the Extremely Large Telescope, or ELT, and this will be the biggest visible light telescope on Earth. Also, near there, there will we will have another facility called the CTA. This will be an array of telescopes focused on capturing gamma rays. Okay, now we have a better picture, so let's travel to the Paranal Observatory. So we will take a look at this animation, and now virtually you are flying over the Atacama Desert in the north of Chile, about 1,600 kilometers north of the capital Santiago, specifically about 130 kilometers south of Antofagasta, the regional capital, and about 90 kilometers north of Taltal, the closest city. So now we are going toward the mountain top of Cerro Paranal, located at 2,600 meters above sea level. This mountain belongs to the coastal range, and despite its altitude, it is located at just 12 kilometers from the coast. And where is the ocean? Well, the Pacific Ocean is located below of this cloud cover. And why those clouds? If right here the sky is so clear, dry, and lonely? Well, this is because of the influence of the Humboldt Stream. This is a cold stream near the coast of Chile and Peru, cooling the atmosphere and causing a phenomenon called thermal inversion at about 1,000 meters above this level, keeping below the cold, humid, and basically bad air for astronomy. And about the layer, instead, we have the hot, dry, and less dense air. So this is like the good air for astronomy. So the clouds are blocked by the coastal range, and near Paranal, the mountains are high enough, surpassing 2,000 meters above sea level. Now, regarding other possible natural barriers around this area, about 200 kilometers to the east, we have the Andes Mountains, with very high mountains, more than 6,000 meters above sea level. So this is another natural barrier blocking clouds from Argentina and Bolivia. So the main result is this landscape, a place with an average of more than 300 clear nights per year, with a very clear and transparent atmosphere, making it ideal for observing the night sky. Also, here we are far away from artificial light sources because of human activity. I mean, light pollution. So, overall, this is one of the best places on Earth for astronomical observations. Okay, right now we will change the view to have an even closer look to Paranal. So, as you can see, this is not an ordinary mountain. And now we can see the different telescopes and structures in the mountain. We are at the summit of Cerro Paranal. So, do you know what Paranal means? Well, in the Quechua language, Paranal means whirlwind, possibly because of some whirlwinds forming in the desert. However, as I told you already, the atmosphere here is extremely quiet. So, this observatory is a true oasis, and you will see how in one of the driest deserts we have a lot of life, and of course, we have a lot of science. Okay, so right now we will change the view to visit the summit of Paranal. So in front of us we have the Very Large Telescope, or VLT. It's acronym. Okay, so if you see the amount of buildings, four giant domes, and other four small and rounded ones. I mean, this one here, this one, this one, and this one. It is clear that the Very Large Telescope, in fact, is not only one, but a very special array of telescopes. So all this facility is the most advanced optical observatory on Earth. So let's take a closer look. So here you can find the four unit telescopes, or UTs, each one with a primary mirror of 8.2 meters of diameter. So the giant ones in your screens. And the other small ones are the auxiliary telescopes, or ATs, each one with a primary mirror of 1.8 meters of diameter. Now, coming back to the big ones, each UT has a name in Mapudungun. This is the language of the Mapuche people, natives from central south of Chile. So here we have the first one, Antu. Antu means sun. This one is Cuyen, and Cuyen means moon. This one is Melipal, and Melipal means four stars, but this is a reference to the Southern Cross, the constellation. And this one is Jepun, and Jepun is a reference to the planet Venus. So this is regarding the names. Okay. Um, Now the small telescopes here, the closer ones here, are the auxiliary telescopes. Now they are very special because they are mobile and they can be moved using a rail system. Do you see? This is a rail system here, and we have different stations here. So essentially, we have 30 stations scattered in this platform. They were specifically designed to work all together as a single big telescope with a variable diameter, able to reach up to 200 meters, as you will see in a few moments in a short video. So why we are using this kind of stations? We will take a look at the video now. So we have a technique to combine light from several telescopes, and this technique is called interferometry. So we are able to observe much more specific details if you compare this with an individual telescope. So thanks to interferometry, we can simulate a giant mirror to distinguish details up to 16 times fainter than a single telescope. So why don't we make small telescopes and combine them to create a huge telescope? Well, interferometry also has limits, and some of the information is lost during its travel. However, it is still an excellent solution to observe objects too difficult to observe with our current technology. So in the animation, basically you are looking at underground tunnels. So the physical light from each telescope is sent using mirrors to the underground tunnels. So the physical light will reach at the same time a single point of combination underneath of the building in the center of the platform. So in this location, we have the main instrument to combine the light and to create a digital picture. Okay, so we are coming back now to the main screen, the main uh, view of the Paranal Observatory. And now you will have the opportunity to visit one of the telescopes. We are going to visit the UT3 Melipal. Now, we can't enter all the telescopes, but don't worry about that because the four ones are identical in size and shape. So the only difference are the instruments inside. So you can, of course, if you want, you can know more about the instruments if you visit the ESO website. Okay, so now we are going to access the UT3 telescope. Okay, so we are now in the inside. So what can you see? Well, this is a giant telescope. Right now we are on the last floor of the telescope at the same height of the main mirror in front of us. The mirror has 22 tons with 8.2 meters of diameter and only 17 centimeters thickness. I am going to do a close-up to look at the mirror. And by the way, the mirror is made from a ceramic and flexible material called Silotur. And the surface of this mirror is a very thin layer of aluminum. So this is basically the reflective surface of this mirror. Okay, so essentially, when the telescope needs to observe the sky, we need to sometimes we need to rotate the mirror, we need to change the position, we need to point to different directions. So essentially, the mirror uh, will be tilted sometimes. So we need to keep the mirror, of course, in optimal conditions to prevent any distortion, any deformation, because the mirror is heavy. Okay, so because of the weight of this mirror, you might expect some deformations or distortions. You need to remember that this mirror, well, is not a typical mirror. This mirror is concave, is like a spoon. Okay, so we need to take some special precautions to take care of the mirror, of course, and we need to be especially careful to take care of the mirror when we are pointing to different positions in the sky. So how can we point the telescope to the sky without breaking it? I will show you this telescope from another perspective to talk about this. So I will show you underneath. And in this new perspective, we are in the lower floor, and we are basically looking at the mirror from underneath. And you can see that the mirror is mounted over this white structure. This is a cell supporting all systems assisting the mirror, and including something called active optics. So in order to understand this, I will do a close up here, and I will show you something. I will show you some gray boxes here. The gray boxes are called actuators. So they are a kind of piston, and we have 150 in total, controlled by a computer. So they are acting on the mirror during the observations in order to keep the optimal shape of the concave mirror. Okay? Otherwise, it could suffer deformations just because of gravity, physics. Okay? So those deformations, imperceptible in a first view, could be critical in the result of the observations. So how is this working together? I will show you again a telescope from the original perspective, so I can explain this better. Now, I will show you an animation. Now, Hector will share some animation to explain something here, because in order to understand how the telescope is receiving light, you need to know that the first step is to open the dome. Of course, this is an exaggerated view of this. So the light will reach the primary mirror first, the concave mirror 8.2 meters. The light will be concentrated, will be reflected to the secondary mirror, will be reflected again to a tertiary mirror, and this physical light will reach one of the instruments. And we have three possible instruments. We have one instrument at both sides. We have another instrument in the bottom. Is like this kind of red, blue, and green boxes. So essentially, we have three possible instruments to analyze the information, and we can use only one instrument per observation. So this is one of the instruments, for example. Okay, you can see that this instrument is a very big and complex, well, camera essentially. Okay, and regarding the secondary mirror, for example, is this one. Okay, so this is the primary mirror. This is the secondary mirror right here. And the tertiary mirror, well, is basically in the middle here, but it's not visible because this is blocking the view. But the tertiary mirror is there. Okay, and in the same well, in this same picture, we can see some engineers working. Okay, because during the day we have some people working on the telescopes, doing calibrations, preparing the telescopes, fixing problems. So essentially, the work in Paranal during the day is for engineers, and during the night the work is for astronomers. So in a few moments, we are going to visit virtually the control room. Actually, we are going to visit the workplace of the astronomers because the astronomers are not physically here at night. During the night, this place is completely empty, is in darkness. Okay, so in this view, well, this is during the day. That's why we have engineers working here. That's why we have the lights on. But during the night, this is completely in darkness, and everything is controlled from another location. Okay, so we are going to finish the explanation here in the telescope because we have to keep moving to the next stop. The next stop is the control building, is right here. In this place, we have the astronomers working at night. I will show you the building from another perspective. So we are going to access here in a few moments. But before doing that, I don't know, Hector, if we have some question from our visitor.
Okay, so we have a few comments. We have ITK12 saying that he's excited for the tour. You have a question from Jess Will from Brittany, asking if we're going to focus on a specific object, instrument, or something from actuality today.
No, it's essentially because we are doing like a fixed virtual tour. We can access only the what is a UT3 telescope, okay, and I can do a general explanation of the telescope and the instruments. But we don't usually focus on a specific instrument. Anyway, if you want to know more information about each specific instrument, you can visit the ESO website to know more. And also because astronomy news are constantly changing, you can also take a look at the press releases of ESO because we have new information constantly there. Um, yeah, but this is this is why we don't focus usually on different things during this virtual tour.
Yeah, and we have a question from Tigrun 1960. He's asking, is that as simple as air pressure? I'm guessing he is referring to the actuators.
Oh, uh, yeah. No, this is I think sometimes I forgot the specific word. Is like an electromechanic. Um, uh,
Like
like
a
I don't
piezoelectric?
remember the specific name. Maybe you can help me with this one.
Okay, so the word that comes to my mind is a piezoelectric, that is a material that you exert pressure and then produce
Yes.
electricity, but it could be the other way around. You apply pressure or electricity and then it produces a pressure.
Yeah, exactly. And the important thing is that this is controlled by a computer. So you don't have an engineer or an astronomer pushing buttons. It's just an automatic process depending on the position, the actual position of the mirror, because sometimes it's tilted, and basically the computer is calculating where you need to provide more pressure to compensate any distortion.
Okay, so and those are all the questions we have so far.
Okay.
Um,
Yes.
I think we can continue, and please, if our viewers have any more questions, any more comments, please feel free to send them.
Okay.
For now, let's just go to the control room.
Okay. Thank you. Okay, so we are going to continue now, and I will keep moving to the control building. So in the control building, we have we have different things. We have offices for engineers. We have some rooms for maintenance, but in the last floor we have the control room. So in the control room, we have the astronomers working at night. So now I am going to show you this specific location because the astronomers are working from here. Um, and as you can see, this place is very similar to any office. So it's not very, like, I don't know, like a futuristic place. It's just an office space. But it's very important because you have different workstations to do the remote control of each telescope. So you have, for example, in this workstation, you have different monitors for different purposes, and you have, for example, Melipal here. So that means that only operations with Melipal are from this are performed from this workstation. So you have a few scientists working here, but they are working specifically on this telescope. Now, in the other side, you have another workstation, but this one belongs to the UT4 Jepun. So only operations with Jepun are from here. So again, you have some people working here, you have many computers, so you don't need a lot of people actually, and they can work from this location only for this telescope. Now, if we continue working in this virtual corridor, I will show you the remaining stations. This one is the workstation for AN2 UT1. So again, we have some scientists working here. Um, Please remember that they need to work all night, and we don't need a lot of people. So essentially, you can expect to have maybe 10 or 15 people working here every night, and they are, of course, in a comfortable space. So you have, well, you have a coffee and cookies and whatever, but they are very comfortable here, and they need to work all night. So this is the last station here regarding the UTs. This is the workstation for UT2 Guyan. So essentially, just to understand the main context of this location, you need to understand that all the telescopes, instruments, and systems explained before are controlled from here. Okay, so during the day, as I told you already, engineers, technicians, and scientists are working to prepare the telescopes for the next observation night. So um, each night we have a telescope operator and an astronomer per telescope. So let me access this control to this workstation to talk about this. So for example, in this workstation, I can tell you that this person is a telescope operator. Okay, so the telescope operator is in charge of the technical details and the movement of the telescope. So he is like the pilot of the machine. And you also have an astronomer. So let's suppose this person is the astronomer. So the ESO astronomer is in charge to direct the scientific observations, and this person will decide the next steps. So he will be like the co-pilot. So the observations are performed by experts from ESO for scientists from all the planet. Okay, so essentially this is what happens here. This is the control room, as I told you. It's not is not a super big space, but it's very, very important because we need to supervise everything from here. Okay, I will come back to the main platform now, because now I want to share something very interesting with you. At this point, you have a lot more information about the observatory and the people working here. But now I want to invite you to know more about the main scientific milestones made from all ESO observatories. I mean, La Silla, Paranal, and Chajnantor. So, in this case, scientific staff from different countries are using the ESO telescopes to study objects near to our home, the solar system, but also others in the more distant places in our universe. So now we are going to explore a list of the top 10 discoveries from the ESO site so far.
Observations with ESO telescopes have led to many breakthroughs in astronomy and, over the years, have been responsible for some truly remarkable findings. Here is our list of ESO's top 10 astronomical discoveries so far. Astronomers using ESO's Very Large Telescope have discovered by far the brightest galaxy yet found in the early universe, and found strong evidence that examples of the first generation of stars lurk within it, stars that were previously only theoretical. These massive, brilliant objects were the creators of the first heavy elements in history, elements that are necessary to forge the stars we see around us today, the planets that orbit them, and life as we know it. ESO telescopes have provided definitive proof that long gamma-ray bursts are linked with the climatic explosions of massive stars, therefore solving an enduring mystery. A telescope at La Silla was also able to observe the visible light from a short gamma-ray burst for the first time, showing that this family of objects most likely originates from colliding neutron stars. Astronomers using ESO's HARPS instrument in 2010 discovered a planetary system containing at least 5 planets orbiting the Sun-like star HD 10180. They also found evidence that 2 other planets may be present, one of which, if confirmed, would be among the lowest mass exoplanets ever found. Newer observations and reanalysis of the data suggest that there could be even more planets around this star. ESO's Very Large Telescope was used to detect carbon monoxide molecules in a remote galaxy, seen as it was 11 billion years ago, a feat that had remained elusive for 25 years. This allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch, and it matched the temperature predicted by the Big Bang theory. The atmosphere around a super-Earth exoplanet was analysed for the first time using the VLT. The planet, which is known as GJ1214b, was studied as it passed in front of its parent star, and some of the starlight filtered through the planet's atmosphere. The atmosphere was found to be either mostly water in the form of steam or dominated by thick clouds or haze. Using ESO's VLT, astronomers measured the age of the oldest star known in the Milky Way. At 13.2 billion years old, the star was born in the earliest era of star formation in the universe. Uranium was also detected in a Milky Way star and used as an independent estimate of the age of the galaxy. The VLT obtained the first ever image of a planet outside our solar system. The planet, which has a mass about 5 times that of Jupiter, orbits a failed star, a brown dwarf, at a distance of 55 times the average distance between the Earth and the Sun. In 2014, ALMA, the Atacama Large Millimeter Submillimeter Array, revealed remarkable details of a solar system that is forming. The images of HL Tauri were the sharpest ever made at sub-millimeter wavelengths. They show how forming planets are vacuuming up dust and gas in a protoplanetary disk. One of ESO's proudest moments came when 2 independent research teams, including ESO staff, arrived at a truly revolutionary finding: that the cosmos is not only expanding, but that it is doing so at an increasing rate. The findings of the separate teams were based on observations of exploding stars, or supernovae, including measurements made from ESO's telescopes at La Silla and Paranal. This discovery was rewarded with the 2011 Nobel Prize in Physics. And finally, several of ESO's flagship telescopes were used in a 20-year study to obtain the most detailed view ever of the surroundings of the monster lurking at the heart of our galaxy, a supermassive black hole. Astronomy is always moving forwards, and ESO's top 10 scientific discoveries are not set in stone.
Okay, so this was the top 10. Very, very interesting, of course. But we have something else. We have one more thing, an additional landmark. Is not so new. It's not new information. It's something that happened a few years ago. A team of astronomers was able to capture the first picture of a black hole. So the Event Horizon Telescope, or EHT, its acronym, an array of 8 ground-based telescopes distributed on the planet, working as an international collaboration, was able to achieve the first direct evidence of a supermassive black hole. The picture will reveal the black hole in the center of Messier 87, a massive galaxy in the close galaxy cluster in the Virgo constellation. This object is located 55 million light-years from Earth, and its mass is about 6,500 million times the mass of our Sun. Okay, so we hope you liked the top 10. This was only a fraction of the discoveries, thanks to the ESO telescopes and the scientific staff behind them. So now we can continue, and from the platform again, I am going to do a very special activity thanks to this virtual tour. I am going to switch the daytime view to show you what happens when you have night in Paranal. So now we are going to observe the night sky from Paranal, and this will be very, very impressive. So as you can see, the sky is almost completely dark, with the last traces of light from the twilight. The moon is below the horizon, and the sky is full of stars. So here we can see some very interesting regions, constellations, objects. So I will show you something that in this case is just next to and to the first telescope here. I am going to show you something just above of and to. And this is a very popular constellation. This is Orion, this one right here. So I will do a close-up to show you this constellation. So Orion is, in the mythology, represents a hunter. Okay, so you can recognize Orion because of those 3 stars there, because they are, let's say, aligned. See, so something interesting about Orion is that this is visible from the northern hemisphere and the southern hemisphere, so you can see Orion from everywhere, and it's very easy to recognize this constellation. So almost everyone can recognize this shape. Now, the 3 stars somewhat aligned here are representing Orion's belt. And inside of Orion, and next to the 3 stars here, we have this interesting object. This object is called the Great Orion's Nebula. Okay, so the Great Orion's Nebula is basically a star-forming region. It's very bright. It's very big. So you can take a look at this object even with your naked eye. So if you are in a clear dark night, you can look and you can notice this object is something like a distorted spot in the sky. But of course, if you try to observe this with some binoculars or even a small telescope, is very, very impressive. So this is regarding Orion. Okay, now we are going to change the position. We are going to move up a little bit from Orion, and we are going to reach a very interesting star. We are going to reach this star. This is the brightest star of the night sky. So its name is Sirius. This star belongs to the Canis Major constellation. Canis Major, in the mythology, represents one of Orion's hunting dogs. So essentially, the constellation of this star, the brightest star in the sky, is connected in the mythology to Orion. Okay. Now, another interesting object I want to show you is located just next to Antu. If we come back to the main telescope here, so if I do a close up here, next to the telescope, you can see another object. Okay, this object here is the Pleiades. This is an open star cluster located in the Taurus constellation. Okay, so this is very easy to recognize, and normally you can notice up to 7 stars if you have a clear and a very dark night. Okay, so the majority of those objects here in this area next to the Pleiades, Orion, Sirius, you can see that they are visually close to this specific area. Okay, this area is very populated with stars. Okay, this area of course is full of stars. This area the same, but this one is very special because you have obviously more concentration of stars. Okay, now this is because when you are looking at this area, you are looking at one of the Milky Way arms, our galaxy, and our sun is only one among hundreds of millions of stars. So during the winter in the southern hemisphere, we can see the center of the Milky Way, and this is another area full of stars between constellations Scorpius and Sagittarius. So one of the most interesting facts about the southern hemisphere is that you can see the center of the Milky Way all night during the winter months. But I mean winter in the southern hemisphere. I mean end of May, June, July. Okay. Okay. I am going to come back here because now I want to change the view to show you a different portion of the sky at night. And I want to show you something here. So we have something very interesting because we have these two things. This is something like two spots, right? So the spots right here are called the Magellanic Clouds. Okay, up there is the Large Magellanic Cloud, and down there is the Small Magellanic Cloud. Well, they are not actually clouds, of course. They are galaxies with an irregular shape, both visible to the naked eye in a clear night like this one. Now, this name refers to the records from Ferdinand Magellan during its circumnavigation of the planet in the 16th century. So at that time, the people were unaware about what a galaxy is. Now, another important area next to the Magellanic Clouds, we can find it here because we have the smallest constellation in the sky. This is the Southern Cross. You can see there is this is the shape of a cross, but it's tilted, of course. And in this case, this constellation is only visible from the southern hemisphere. Okay, so you cannot see this from the USA or from Europe. So what happens here? The Southern Cross, as I told you already, is the smallest constellation in the sky. But it's also very interesting because it's like a natural assistance tool to find the South Celestial Pole. So what is the South Celestial Pole? It's basically a projection of the South geographic pole in the sky. So in the northern hemisphere, northern observers are able to find this north celestial pole very easily because they have a very bright star next to this point. It's called Polaris. But in the southern hemisphere, we don't have any bright star. So our solution to find the south celestial pole is to use the southern cross. So in order to find the south celestial pole, we need to project in our head the longer stick of the southern cross. So if I do this now, like 1, 2, 3, 4.5, more or less like here, you can find the south celestial pole. So that means that if you take a long exposure astrophotography toward this direction, you will find a lot of circles. Okay, and all the stars will appear to revolve around this point. Okay. Also, if you look at the horizon, specifically from this point, if I outline a line, to the horizon, you are looking essentially to the south cardinal point. Okay, so that's why it's so nice to know how to identify the south celestial pole. Okay, I will finish this um, tour during the night time at the Paranal Observatory because now I need to come back to the daytime view because we have one last stop before finishing this virtual experience. And in order to show you this, I have to rotate the view because I need to show you the the base camp, the Paranal base camp, and this base camp is located here at 2,400 meters. So in this area, I want to show you specifically a very special facility that is called the residence. Okay, first you have the base camp here. You have a lot of interesting facilities. You have some rooms for contractors. You have a mirror maintenance building. You have a warehouse. You have some offices for informatics. So you have a lot of interesting things here because this is something like a mini city. And you have a lot of people working here. You have more than 130 people. So they need to stay here and working on a shift system. Okay, okay. So now I want to show you the last stop of this tour, and the last stop is the residence. So the residence is essentially a place where the ESO staff can stay and rest. Okay, it's the home of the ESO staff when they are working in the desert. So essentially, you need to access using this ramp, and this residency is not exactly underground. It's just taking advantage of the shape of the land, because in the opposite side you have a regular wall with windows. Okay? So you need to access using this ramp here, and now I will show you the inside, and it's something like this. Okay? So here you can see the workers can enjoy a more humid air. They have a swimming pool, they have green areas, and some rest. If you compare the desert, the intense sunlight. So this is of course much more comfortable, and you have other interesting things here. You have, for example, the restaurant over there. All people working in Paranal can go and eat there. You have something like the lobby and the reception. So this is essentially like a hotel, but only for the staff. So this is the main difference. Okay, so with this view of the residence, this very beautiful place, I want to know if we have some last questions from our virtual visitors. Hector?
Okay, so we have a question here. How many gigabytes of data do we collect per night?
Uh, well, we have technically you can get way over 100 gigabytes per day per night, and usually you have maybe even 300, 400 gigabytes per night, even after compression. And when you, well, I think it depends on if you are doing a heavy use of the instruments, uh, because this will give you less or more data. But essentially, you can expect easily to collect something like 400 gigabytes per night. Maybe you, Hector, you have more experience with working with a specific instrument, so you can maybe give some insight about this.
So the instrument I'm most familiar with is Muse, and the data cubes of Muse, as we call them, each of them can weigh over 1 gigabyte easily. And if you combine many different of them to make a single larger field of view, even more so. So, so like the current data cube that I've been using is, I think it's close to 100 gigabytes, but it's a lot of data cubes combined into a single file that you can easily handle. So yeah, it can become quite heavy in terms of space. We have a lot of comments telling us how beautiful the night sky is, but I have here the next question is from TR-Goon 1960. The mini city, does it have a special control over heat loss so as to not interfere with astronomy?
Well, I suppose this is related to what light pollution, first thing. And if the question is specifically talking about the heat, well, you need to consider first that mountain top is 2,600 meters above sea level, and the base camp is located at 2,400. So you have an important altitude difference. So the heat will not be a big issue actually, and it's not like you have a lot of different facilities, and it's not that you have a lot of different machines doing, I don't know, creating heat during the night. And regarding light pollution, for example, everyone in Paranal is very aware that they need to close the curtains all night. This is very, very strict. The cars can drive only with parking lights. Okay, so you need to be very careful when driving at night, and you have no lampposts. There are no lampposts at all at Paranal. So when the people, for example, are, let's say, working in Paranal at night, they are allowed to use a flashlight, but they need to point strictly to the ground at all times. And this is how they are basically keeping under control light pollution. So you don't have any light pollution at Paranal. And regarding heat, as I told you, well, you don't have any important source of heat during the night. And but as I told you already, you have an important altitude difference between the base camp and the summit.
Okay, thank you. I'm not seeing any more questions. So to finish, let me just ask you, maybe you could tell our viewers how to visit in person Paranal Observatory.
Yeah, so you have a public visit program, and people can visit Paranal every Saturday. We have two possible tours, 10 a.m. and 2 p.m. Each tour is about 2 hours and a half, and you need to do an online booking if you want to visit Paranal. The visit is totally free, but you need to reach the observatory with your own means of transportation, and the closest city is Antofagasta, so you need to consider something like 1 hour and a half travel time. it's always better to consider like 2 hours of driving better, because you need to arrive in advance of the tour, and you need to do this online booking in advance as well. So maybe at least 2 weeks in advance. But yeah, you can visit Paranal if you want.
Okay, and with that, I think it's time for saying goodbye. For my part, it was my pleasure to be here with you today. So I remind you that we are doing these virtual tours every Saturday. We are alternating between Paranal Observatory and the Sea Observatory, and also between Spanish and English. So keep an eye out for when the next tour is going to be and in which language.
Okay, thank you, Hector. And well, we remind you that all these visits, information, and pictures are available on the ESO website. And yeah, and we will alternate between Spanish and English, Paranal and La Silla. So I hope you like this virtual experience. So please stay alert to the ESO social networks to know when we will have the next tour. Also, on behalf of ESO, I want to say thank you very much for your presence and goodbye.